I'll have to stand here to use the microphone. Yeah, so first I'd like to thank the organizers for putting together such a nice workshop and inviting me to come again. I enjoyed myself quite a bit last year, and again this year it's been very intellectually interesting and stimulating. And then, yeah, thank you for attending after the banquet last night. The last day is always a little tricky sometimes for people to get up in the morning to see the first talk. So thanks for coming. So yeah, I'm going to talk to you today a little bit about the kind of work we've been doing at NIST in developing detectors. And primarily, so we actually have been developing two kinds of detectors, but I'll focus primarily on the nanowire work. And it's actually been a huge effort at NIST, actually, and I'm lucky enough to represent the work of a lot of people. The names that are on the left column are the people that I work with most directly in my group, who I co-manage with my colleague, Rich Mirren. And then the other people in the second and third column are people at NIST who we've collaborated for a variety of reasons, whether it's interesting new basic physics or whether it's really trying to understand how to measure the detection efficiency of our detectors. Once you start making high efficiency detectors, then calibration gets more and more tricky. We're fortunate enough in Boulder, Colorado to have basically the people who do the calibration of optical power meters. So that's really convenient to go talk to them. All right, and then I have a lot of collaborators, which I didn't list all of them, but I think at some point probably little bits of different collaborative work may be talked about in my talk. And then I should acknowledge I get a lot of support outside of NIST from other parts of the US government. All right, so what I'll talk about quickly today is a little bit about why NIST is interested in it, and give a little bit of introduction, because not everyone in the audience might be familiar with how one uses superconductors to detect light. So I'll try to go through how the nanowire detectors work, and then I'll jump into our more recent work in integrated optics, talk about this new kind of device design that I've called the bilayer, and then I'll talk about a new wavelength regime we've been looking at, which is the UV. Then I'll talk about what we actually are doing now in the lab, and give you some progress reports on how do you get towards a megapixel array, and how do you make these detectors more usable by hiding the cryogenics as much as possible. All right, so NIST has a long history, well, I shouldn't say long history, a recent history of work in really trying to measure individual quanta, whether it's electrons, superconducting flux quanta, or looking at individual ions, or trapping atoms. And the group of people I work with, we look at single photonics or faint photonics, and trying to really develop a toolbox for not only making and generating generating faint amounts of light, which I won't talk about, but measuring, generating, manipulating, and then measuring them in interesting ways. And today I'm going to focus on the measurement part, and yeah, there's a lot of things I could talk about if you want to hear more about the other kinds of measurements that we do at the single photon level. All right, so when you talk about a single photon detector, you really need to understand, I think, the application you're going after. And one of the first things you need to understand is the wavelength that you want to make your detector for, or that you need to observe, is that something that can be done? The wavelength range really can decide what kind of single photon detector you can use. Another really important aspect for a lot of people is the detection efficiency. How efficiently can you see the light? And at NIST, I've been really pushing this concept of system detection efficiency. It's one thing for the detector design or the detector physicist to say, oh, my quantum efficiency is 99%. It's a different thing for that kind of efficiency to be used by a non-detector expert, and whether you can actually get 99% of the signal that you've made in the lab detected by this kind of new single photon detector. The other, of course, interesting thing is you do want to have very few false positives, so very low dark clicks or dark counts. But one thing to recognize is that A source of background counts can just be the fact that your experiment is at room temperature and it emits black body radiation. So one interesting thing to think about is that may mean that if you really want low dark counts at, let's say, 1550 nanometers, your detector has to be a refrigerator, because otherwise it's going to be exchanging 1550 nanometer. If it's at room temperature, it's exchanging 1550 nanometer photons with the environment. But if your detector is really cold, it's not really ever going to emit 1550 nanometer photons. It's just going to absorb them. So at room temperature in a single mode, there's a roughly maybe 3,000 or so, a few thousand counts per second in a wavelength range between 1550 and a couple microns. And so one has to be aware that there is this background flux potentially of light that's just due to the fact we are emitting photons. Anyway, so that's one little maybe bit of physics to think about. There isn't going to be much physics in my talk necessarily, but that's something to think about. And then, of course, you want to have very low timing jitter. You want to know when the photon arrives, because that's a way of rejecting potential background. And then you want to count as fast as possible. So these are interesting metrics to think about in terms of the technical performance of your little widget and how good does it need to be. And then other considerations that if you're a detector physics person, you don't normally think about, because you're just worried about getting your little device to work, but in terms of getting other people to use, you really need to think about whether my detector packaging is something that's compatible to an end user. And so that's something that we've spent more time on at NIST, is really trying to understand how to do the packaging in a way that the detectors that we've developed can be used by non-experts. All right, so here's just a quick table. And this is not meant to be completely 100% accurate, because this table is evolving rapidly all the time. But I tried to summarize some of the different technologies out there for detecting single photons. You've got maybe the pointer's dead. All right, so one of the first styles of detectors was a photomultiplier tube. It can be used, from the UV down into the short IR. Silicon, which is a fantastic material to make a detector out of, can have very high efficiency. But what I'd like to point out at the bottom is there's been some really interesting work coming out of Dartmouth University on something called the quantum imager, the QIS. And I put the reference for that right here, this last line. I encourage people to go look at this. It's a really interesting kind of detector. It's kind of like a CCD. It's single photon sensitive, though, and it has some really nice properties. So. And then on the right column is what typically people have done with superconducting detectors, whether it's a transition sensor, which I won't talk about, or what we'll focus more on today are these nanowire detectors. And I'll briefly describe how these nanowire detectors work. So, thank you. Can you hear me? All right. So just so that people understand, if you're not familiar with superconductivity, and I want to try to explain how these nanowire devices work. There are a few properties that you need to know about superconductors to understand how they work. The first is that there's a critical temperature where if you drop below the critical temperature, the resistance goes to zero. That's an important concept. The second concept is that for nanowire detectors that's important. The second concept is that there's a critical current density, or a maximum amount of current that the wire or material can conduct before it becomes resistant again. So you can't have infinite amount of current flowing. There's a finite amount and a finite current density. So maybe around 16, 17 years ago, a group in Russia demonstrated that you could make a really fast single photon detector. And, it was an APL 2001. And what it really let you do is when you deposited enough energy in this nano structure, you could break the superconductivity locally and get a pulse, or get an electrical pulse telling you that there was a photon that was absorbed. And it really, it's a digital detector, so it just tells you, yes, there was energy deposited. It doesn't really tell you how much energy, there's been some energy deposited. So briefly, how it works is let's say you've got this wire, and current's flowing through the wire, and then a photon's absorbed somewhere in the middle of the wire, maybe off to the side slightly. So this is the electrical circuit. you bias current through it. You've got the current, and then you've got the superconductor, which I've drawn as an inductor. It turns out that in a lot of the superconductors used for nanowire detectors, they have an anomalously large inductance. And so we often draw in a circuit diagram the presence of the nanowire as an inductor. So you've got current flowing through the nanowire, and then you've got some kind of impedance due to your transmission line / amplifier. So current's flowing, and then, the energy of the photon's absorbed, it breaks the superconductivity, and you get some normal region or resistive region. And so the current that was flowing through here gets diverted to your amplifier or your readout chain. So most of the current then stops flowing through the device and goes to your amplifier so you can detect the photon. And then, because the current's no longer flowing, you don't have very much joule heating, the superconductor can cool off and the superconductivity can get restored. But one thing to remember, though, is that you don't build up the current instantaneously. It's going to happen with this L over R time constant. So the recovery time that you see often in, let's say, electrical pulses from the nanowire detectors is really the decay time, or the falling edge or rising edge of the pulse, whatever you want to, however you have your scope set up, is due to the current building back up into the superconductor. It really isn't the thermal recovery time. The thermal recovery time is actually much faster. All right, so one of the things that we did at NIST, which is different than the initial people who were in the field of nanowire detectors, is that we switched materials. So the conventional material being used, and it's a good material, it's a fantastic material, is niobium nitride or niobium tinitride. But at NIST, we were concerned about trying to figure out how to make detectors that could work on almost any kind of substrate. And one of the things about this kind of material is that I think it's best if it's polycrystalline, or you get the right combination of structure on there to get good superconductivity in this material. But what we tried at NIST was we decided to explore a new class of materials that are basically amorphous alloys. So you didn't need a special substrate to make high quality devices. And there's been a lot of materials work now that you don't need specialized substrates for the niobium nitride or niobium nitride family of materials, but we went off in a different direction. And what we like about our material is that it's amorphous, so you don't have to worry about the crystallinity structure of your substrate. And we think we can make really large devices, large area devices, and we have, I think, better yield potentially. The drawback is that it requires colder temperatures. And so from a cryogenics point of view or system integration point of view, that could be a deal breaker. That, instead of requiring, let's say, 4 Kelvin operating temperatures, we require maybe 2 Kelvin or sometimes even 1 Kelvin. And so from a systems point of view, that could be a huge disadvantage. But it really depends on the kind of system you build. And maybe close to a decade ago now, using our amorphous materials, tungsten silicide, we were able to make a system where the system detection efficiency was over 93%. And so we've been able to do a lot of interesting experiments in quantum optics and quantum information as a result of making some really efficient detectors, even at 1550 nanometers. Thank you. All right, so we're going to switch gears and talk about what we've done most recently, which I think, I forgot to put the reference out. We have an archive posting from last year where we talk about integrating our nanowire detectors on silicon nitride waveguides. And so what's interesting about this is that actually these waveguides were not made with e-beam lithography. So normally when people have been making these nanowire devices, the line width typically has been on the order of 100 nanometers. But because our material is high enough quality, it turns out we can actually get away with 300 or 400 almost nanometer wide wires, which can be made with a little trickery in the clean room to make high quality detectors that have a saturated detection efficiency. So I didn't explain this plot, and I'm sorry about that. What this plot here is I've got a plot of the current that's flowing through the device on the x-axis, and sometimes detection efficiency or clicks per second we see on the y-axis. And what's nice about this curve or seeing the data this way, what you want to see in this kind of device is you want to see this plateau, where the efficiency or the number of clicks that you see as a function of the current that's being applied is constant. That really means you basically reached the limit, or you saturated the efficiency that you can get from your detector device. The fact that you see a plateau is a good sign. It means there's margin. You don't have to bias way at the highest current to get the most sensitivity or the highest efficiency. It turns out you can back off at a slower current bias and see basically high efficiency. And having that margin is useful. You can play with that margin and sacrifice that margin for other things. So, for example, one thing you could sacrifice is to say, oh, I don't need to be as cold. If I run my refrigerator a little warmer, the bias plateau will shrink a bit, but I'll still be able to get high efficiency. So you can trade a lot of things in your system if you've got a nice plateau to work with. So that's a good sign that we could make nanowire detectors on waveguide, silicon nitride waveguides. And this is us showing different kinds of experiments where we've integrated the nanowire detector with, let's say, a Mach center interferometer or ring resonator filters. And instead of, these are pretty standard kind of curves one sees characterizing, let's say, Mach center interferometers or add drop filters. But the axis is different. The axis is, instead of being dB, because we've hooked it up to a power meter, it's now counts per second, because we're now measuring the performance of our silicon nitride optical, photonic circuits using our nanowire detectors. And because the nanowire detector has such great signal to noise, or the fact that the dark count rates can be quite low, you actually can get a larger dynamic range characterization of your optical components. So what's not, for example, something we've done recently in our group is verified that we can actually filter, let's say, pump photons that are being used to generate pairs in microrings. We can filter them with like 100 dB stack of, or a few, well, we can filter them to 100 dB or so, filter out the pump to 100 dB. Because, if you look and use a regular power meter, the dynamic range of a conventional power meter is about 40 or 50 dB. So to check that you have 100 dB of filtering is impossible with a conventional optical power meter. All right. And then one thing that we've thought about a bit is how do you actually get light onto your chip? And this is one of the schemes that we've developed. In photonic integrated circuits, people often look at grating couplers, and you need to have the light come in at a certain angle, and we've tried to develop a way to efficiently in the sense of time, couple light from the fiber into our grating coupler without having to spend a lot of time with, let's say, cryogenic positioners or things like that. Just figure out a way to passively align and glue it in place type of line. So this is a picture of what we've developed recently. All right, so I want to switch gears a bit and talk about something else, and that is we've been thinking about different ways to, let's say, fabricate our nanowire material in a way to enhance the efficiency. And one thing that happened when we were trying to make arrays of detectors is we realized that the nanowire detector, if you had two nanowire detectors fabricated right next to each other, so within a few hundred nanometers, it turned out when one nanowire detector fired, the neighboring one would also fire. There would be the heat from the breaking of the superconductivity in one nanowire could propagate to the other. And for arrays, for closely dense packed arrays, that's bad. But okay, so that's bad. We've been trying to figure out ways to reduce that problem. But one thing that happened was Verma, the person who leads our nanowire detector work, realized we could use that to our advantage. And what we could do is we could just actually stack now two nanowire detectors, or two nanowires, stack them on top of each other and use that to enhance the absorption. So what you see here, this is a TEM picture, so this is epoxy because they did a cross-sectional TEM. What you see here is amorphous silicon, which is a protective cap layer, and then our amorphous superconductor, which is tungsten silicide, and then another thin layer of amorphous silicon, which insulates these two insulates the two nanowires from each other. And so what you can do when you think about that is now you can use the fact you can stack different nanowire detectors together so that if you get energy deposited in one layer, the heat can translate to the other and break the superconductivity in both layers. And you can effectively make thicker stacks of this nanowire material. And so when you think about it from a optical design point of view, oftentimes a variable you'd like to adjust if you're really optimizing the stack of materials to get really high efficiency is sometimes you want to adjust the thickness of the absorbing region, because it could turn out when you do the optimization that slightly thicker detector material will give you higher efficiency. So that's something we were able to try to do. This is an example of the count rates that we saw in say, the top layer nanowire device as a function of current in the bottom layer and vice versa. These are different count rates. And we were able to show in this APL that we can actually get clicks in one and then cause a click in the other simultaneously. And so what that really lets you do is make some really high efficiency devices. So this is an example of us taking this bilayer concept of a nanowire absorber region, putting it inside a stack. In this case, the stack is a dielectric mirror stack underneath the device. Let's say an AR coating on top. So if the light comes in from the top, there's an AR coating. It likely is to get absorbed in the bilayer region, and then if it doesn't, it goes through, gets reflected, comes back up, and this is a very weak cavity. But the nice thing is that because we have this bilayer absorber, we actually broaden the expected response in terms of efficiency. So this is from 1400 nanometers to 1700 nanometers, we're seeing close to 90% efficiency. So the dashed line is what we calculated or expected to see. The 90%, this red solid line is a let's say, this calculated subtracted by 7%. We have some missing 7% we can't account for. But what you can see is that the efficiency is flatter than what you'd get if you just had a single layer device or a single layer in the middle. So you can actually broaden the efficiency over a wider range of wavelengths because we've got this bilayer material in between. All right, so that's one thing we've done. And then the other thing that's been happening is we've been working with Dave Wineland's group to understand whether we can integrate nanowire detectors with ion traps to enhance the way they do their state detection in ion trap quantum computing. And one of the things that's unknown, or wasn't known until we started the work, was whether we could efficiently detect the 313 nanometer photons coming from their ions. The other challenge is when you do the readout, there's an RF electrode. When you do a readout of ions, there's an RF bias that's required. And that one thought was that could really affect whether we can get high efficiency detection. What's not known is whether the presence of our nanowire detector is going to affect the motional heating of the ions, which is the source of decoherence. And one thing that we verified is we were able to operate our nanowire detector at 3 Kelvin, so it could be compatible with the temperatures that the ion trap group was running their later generations of ion traps. So here's, I think it's definitely on the archive. I think it's going to come out in Optics Express momentarily. This is an example of the kind of thing that we've been fabricating. So our nanowire detector is in here. It's in green. The RF electrode, which is a potential source of problems, which I'll describe in this curve, is in pink. And then these gold colored wires are actually the leads. And so this is the nanowire. This is the blow up of this region. This is the nanowire. This is the gold electrodes as we normally deposit. And then this is electroplated gold that's used when fabricating the ion trap. So it's a complicated fabrication process where we go in the clean room, make our detectors, and then it comes out of the clean room, it goes into a plating shop where they literally put electroplated gold on top of everything we've done in the clean room to try to integrate the ion trap structure with our nanowire detector. So this curve is the bias versus efficiency curve, or counts per second curve that I was talking about. And then this is where you can see the advantage of having this plateau, because what's happened when we turn on the RF is that it induces too much noise in it induces current, I shouldn't say noise, it induces current on the biasing of the circuit that we can't bias as high as we'd like to get the high efficiency. That the RF on top of the DC current biases causes us to falsely click sometimes. So we have to turn down the current bias, and that reduces our efficiency. But it's not so bad. Actually, so when we turn on the RF, it goes down to here. And then with some clever electronic circuits, we can try to cancel the RF, that current that's coupled into our bias circuit, and we can recover a little bit of the counts per second. So this is an area of research really in terms of trying to understand how to electrically, let's say, cancel the effects of the RF bias here by cleverly applying RF onto our bias lines. And hopefully not affect the ions that are doing the quantum computing. But that's, well, that's literally work in progress, and hope we have some good results soon. So I want to shift gears again and talk about, is there a way to get a megapixel array? So there's actually, I think there is, and there was this really nice paper that appeared on the archive from the MIT group, where they made an imager based on a, it's a pretty old concept, based on a time of flight, where there were detectors made, I think, to detect X-rays possibly. I go back and think about it. But it was based on the time of flight, that when the energy hit some wire, you could get an electrical pulse, and the pulse would go to the right or to the left. And if you measured the time arrival at the two ends and took the difference, you could figure out where the energy was deposited. And so what the MIT group did is they scaled that idea down to the nanowire detector structures and embedded the nanowire effectively in a transmission line. And so there's this, you can make a very long transmission line, time when the photons get to the two ends, and then determine where in the wire the event occurred. And so we've been making these type of flight imagers. It turns out to match well to the kind of readout electronics we have to really time the time of arrival. We have to transform this meander, which turns out to have about a 2 kilo ohm characteristic transmission line impedance. We have to transform it to 50 ohms, so you can read it out efficiently. Part of the reason one likes this 2 kilo ohmish impedance is that it just turns out that the inductance per centimeter with the, let's say, stray capacitance per centimeter, that really tells you the speed of the signal propagation, the speed of light. And because of the anomalously high inductance per unit length, that means the speed of the signal here is really slow. It's like 1% or possibly 0.5% of the speed of light. So because it's so slow, the timing, you actually can pixelate this to a lot of pixels and possibly a megapixel. So that's something we're trying to explore. And this is a CAD drawing of a 2.5 millimeter by 2.5 millimeter nanowire that we're going to try to use to image UV photons. And then, unfortunately, you can't tell, but this is actually the device, actually the leads, the transformer lead right here is, this is actually a fabricated device. So this is actually cold and being tested right now. All right, so that's something interesting, a megapixel array. I think it'll be really exciting if we can actually get single photon counting at whatever wavelength we like at megapixel scales. And then the other final thing that we've been working on, I talked about briefly last year, was trying to figure out how to make a very compact cooler. So really the reverse, I would say, of what we heard, I don't remember if it was yesterday or 2 days ago now. It's all a bit of a blur. Instead of trying to make a 5-watt cooler at 1 Kelvin, we're trying to go in the other direction. Make a cooler that's really small, that can cool a handful of devices, maybe 16 or so. But cool it in a package where it's invisible, that you don't even know that it's a cryogenic device. It's in an instrumentation rack, maybe it's 6U tall. That's a jargon of instrumentation rack units. So maybe the equivalent of like your tower PC, or maybe 2 tower PCs stacked on top of each other. That kind of size, and taking about 300 watts. So what's interesting is we've done a lot of work already for the last couple of years. And so we've got the cooler actually working. So this is the actual business end of things, where the area right here gets to about 1.7 Kelvin. And so it can cool 20-ish so nanowire detectors, and only uses a few hundred watts of power. So you don't, you're not going to break the bank in terms of your electric bill. And then it's done in a small size and using a new kind of compressor, actually it's not a new, a different kind of compressor, where you actually don't hear the sound. It's at a frequency range where it doesn't make as loud a noise, and you're not going to get a headache from this 1 hertz or 1.5 hertz thing constantly, making that expanding gas noise. So this is something that we're hoping to finish by the end of the summer. And if you're lucky, you might get to see it if you come to Boulder for the single photon workshop, which is later this year. So let me just end by saying I think superconducting nanowire detectors have really unmatched performance in a lot of different metrics, and the combination of which makes it really good for quantum information processing. We've been trying to really understand how to improve the efficiency beyond the 93%. We're still stuck there, and there's a lot of interesting reasons why, and we're trying to understand why. I think there are a lot of interesting new applications that people are starting to explore. I'd like to emphasize that really the fundamental limits of how well nanowire detectors could perform are not really understood, and I think it's an area of research I'm interested in, and I'm hoping other people will really get into that. Packaging is still a challenge for a lot of people. It's, the fact that it runs at cryogenic temperatures is a real turnoff for a lot of people, but we are working on trying to make that invisible. And I'm starting to get excited about the prospect of making megapixel class arrays and truly trying to understand the new kinds of electronics that one would need to read those arrays out. And then I'd just like to end with a small advertisement. I don't even remember which number single photon workshop this is. 7th maybe? Anyway, this year it's going to be in Boulder at the end of the summer, and I encourage you, if you can, to come and maybe even give a talk. So, thank you.
Okay, so we have time for a couple of questions.
Thank you. Yeah, thank you. So I'm really interested in the megapixel array.
Sure.
There's a maximum, I guess, to the width of the nanowire that you can practically use, which sets a maximum packing density. And yeah, and then you've got some considerations as well, like this thing is obviously not going to be like a 1/4 inch CCD size. So that then sets some interesting questions about how you form an image on this thing, and what Gaussian optics allows you to do. So can you talk a little bit about sort of applications for this and how you might use it as an actual imager?
Sure. So you're right. So there are some interesting issues about packing. Well, so one thing I would say is that we do think you can actually densely pack the wires back and forth. So this particular design that you see is it's like, say, a 20% fill factor. So you've got, let's say, for this particular UV detector, it's 500 nanometers wide, and I think it's on the order of 1 micron spacing between them. And so in the UV, that doesn't turn out to give you a really high efficiency because the wavelength of the photon can go through the gap. But I think you could do similar things at, let's say, 1.5 microns, where the fill factor is closer to 50% or something. And then you can get pretty high efficiency. One thing, though, you're going to have to be careful about, and one thing we haven't really worked on yet, is that your pixel is not going to be square, let's say. It could be rectangular. You could have, because of the timing, it's going to be very narrow. It'll be very narrow in this direction, but then fat in that direction. But one could rearrange the structure so that it meanders in a square pixel and then goes to the next, meanders in another square pixel. So that's a structure we've talked about in our group meeting, but we haven't fabricated that because that's way more complicated to fat than just a simple meander. So you're right. There are a lot of imaging issues to think about in terms of is it going to make can you construct an imager that people are going to be familiar with using? In the beginning, probably not. It's probably going to be a lot of reconstruction, but hopefully eventually we'll get to the point with the fabrication where we can make stuff that people are used to, where it's literally square pixels effectively covering the area.
Hi there. How would you model your circuit in a lumped circuit diagram of your bilayer inductors?
So that's
I assume that they're electrically isolated as well, right?
They are. They're electrically isolated. So that's tricky. Well, it's not really. It's straightforward, I would say. It's a little tricky, but You know, effectively it is this. It's a pretty simple SPICE circuit. You would have to make, yeah, it's effectively this with maybe a little trickery with what happens when a photon's absorbed in the thermal recovery, but those are all pretty simple SPICE elements one could create. And actually the group at MIT, I think they're willing to share with people their SPICE model. We have our own model we've been trying to refine, but it's an L/R circuit, and there's a little bit of current controlled resistance and switching.
Would you get capacitance between the multiple inductors?
Sure, there is some capacitance, but that capacitance actually is, the resonance frequency of that is really high. It's way higher than the time scales of this circuit.
Okay. I think in lieu of the time scale, people have to hold the questions. We have to continue with the session. So let's thank Sae Woo again.